All right, so we're on to the second set. This next lecture, we kind of covered what a hypothesis is, what a null hypothesis is. Those are really good, important concepts to know. Basically, that null is nothing's going to change, and usually your biological hypothesis is the opposite, where you're going to say something is going to change. So this is the Stanley Miller experiment. This is a good experiment to show that when you add these organic molecules together, you can ultimately get out through the kind of combination of electricity, heat, water vapor, and these chemicals. You can actually find organic precursors in those. So it's a good exercise in how certain you can be about certain amounts of data, things like that. But for the most part, it is just a good example of how those key organic molecules kind of first showed up. But I'm not going to ask you to recreate that or anything. This is just an example of how scientists still eliminate uncertainty. Scientists, doctors, biggest thing is a drug curve. So, on to pH. So pH is essentially a measure of how acidic or basic something is. If you are acidic, you have lots of these ions, these H plus ions. So remember, this is just a hydrogen without its electron. That's why you have a positive charge. Over here, basic things have OH ions, and they're very high if you're basic. Remember, this is like a Richter scale. At 7, everybody's neutral. There's equal amounts of acid and base, and nothing is like hyper aggressive. Every time that you go down, though, to the new one, or to like a lower one, you're going to go up times 10 the amount of these hydrogen ions that you have. And then times 10 again, for example. So all the way from 7 to 5 is 100 times. There's 100 times more of these ions. Now, the same is true over here for these OH ions. However it helps you to remember this is going to be your best way of doing so. There's not a strategy that works for everyone. For me, it's basically that I just keep track of how many of these are running around, and I just remembered that they are going to be in opposite of these OHs. Because one important concept to keep in mind is that when you put OHs and you combine them with these hydrogens, the only thing that's going to form is just more water. And things will just get back to neutral. So for example, if you put a solution of 4 with a pH of 4, and you put in a solution of 1, 2, 3 of 10, if you put these two solutions together, they would cancel each other out, and you'd actually end up back in neutral, because they just combine to form water. And this graphic is just kind of showing that, is that if you combine these, you're just ultimately going to get water, because although these are dangerous in large amounts and in excess, they cancel out pretty easily. So this is a good set to know right here. This whole basic concept will definitely apply to things that we'll see on the test. So when we're talking about an acid, it's basically anything that immediately donates a proton, or this little H plus ion. Because remember, if this is a hydrogen atom, hydrogen only has one proton and one electron, and if you don't have that electron, you're just a positively charged proton. So you can call this an H ion, a hydrogen ion, you can call it a proton, it doesn't matter. Anything is an acid that is going to shed this into solution, basically. And that's what happens here with this chlorine, is that it basically just steals that extra electron right here, visualized here with that negative sign, and then it just exists fine. It doesn't need to bind anything, so it just sheds and kicks out this hydrogen over here. Same thing is going to happen with something that's basic. So sodium that's semi-bonded to this OH group, the sodium's basically just going to shed this and like give away its electron over here, and that's what we see with that negative right there. So we give away that electron, and then the sodium is just happy to exist as an ion with a plus charge, because remember, now it's filled those 8 electrons in that outer shell. So it wants to exist as a plus, and it just sheds off that OH. So anything that donates an OH, that's going to be a base. And this scale is kind of what I was trying to show you up there, is that if you're at 7, you're at neutral. And each step down is 10 times worse. So if you're 2 down from 7, you're 100 times more acidic. You have 100 times more H plus ions, and they're just saturating everything. Now you can view the pH scale just purely with how many of these ions are around, or every time you go up in pH scale, you can know that you're getting a lot more basic. So while there's less hydrogen ions here, anytime you see less hydrogen ions, that's going to mean more OHs. So pretty much there's always going to be a relationship between how many hydrogen ions there are and OHs. So if we go back up here, remember, the more hydrogen ions you have, the less OH ions you have, and the opposite is always true as well. So we saw that these can basically degrade anything that's in their way, all these little charges, these little positive charges, or sometimes if it's a basic solution, they just rip everything apart because they're too highly charged and there's too many of them. That's why we saw those cans basically melt. So this is what a buffer is. So if we have a strong acid like an HCl, it's going to immediately donate this H into solution. What happens is that this MSG, which is a buffer, it starts with oxygens that have these little minus charges right here. And what that does is immediately attracts this positive H over here, and then they bind up and everything's canceled out then, right? So essentially, so remember, we're just starting right here with this O, with this oxygen. If it has a negative charge, it can take a positive proton over here, this hydrogen ion. And that's all a buffer is. A buffer is essentially just something that is going to soak up all of these ions right here, okay? So anytime you have a buffer in solution, it's basically going to keep everything neutral as possible. It's not going to let the pH change, essentially, because it's going to gobble up all of these things, all of these little hydrogen ions that are going to go into solution. So this was the example we talked about in class, how when certain things react and certain acids react, sometimes in this case we react with water, you end up with a free ion, a free hydrogen ion. And then the more of these that you get, the more everything becomes acidic. And that's the basic concept. All right, van der Waals, this is basically just a chemical phenomena that there is an inherent attraction between elements. You do not need to know this on the test. Everything's going to be fine as far as this. It's good to know for chemistry later on, and just we'll kind of see this in some of the future lectures. Okay, and then this is just carbon bond reviews, so nothing too special here, but it's a good resource. This is a good side-by-side covalent versus ionic with some great compare-contrasts here. I would definitely take a look right here because it's very fair game for me to ask you, or at least incorporate the content of, is this an equally shared covalent bond, or is this an unequally shared ionic bond where you've got a negative and then a positive charge, right? That's good. You can also practice some of these rules for how much things can bind. You can take a look at organic molecules. You can work on your shorthand, because you will often see things written like this, and especially even in this class. But you know, for the most part, we're not going to test on writing in this shorthand, but future classes and pre-health stuff,